In the mid-1960s, the glowing cathode ray tube screens monitoring British airspace were dangerously cluttered with thousands of fast-moving blips. Operators in high-stakes defense installations faced an alarming operational bottleneck, communicating precise location coordinates quickly to military mainframe computers. The traditional interface of mechanical buttons, bulky trackballs, and imprecise light pens was simply too slow and error-prone for high-stress air traffic control. A faster, more direct human-computer connection was urgently required to prevent catastrophic collisions. Inside the quiet research laboratories of the Royal Radar Establishment in Malvern, England, a visionary engineer named E.A. Johnson recognized this fundamental limitation. The National Defense System required an intuitive, frictionless method for human operators to select target aircraft directly on a glass display surface. Johnson realized that the human body itself possessed a unique electrical property known as capacitance, capable of bridging the physical gap between human thought and digital machine architecture. In 1965, Johnson published a revolutionary two-page paper outlining his theoretical breakthrough, the world's first capacitive touch screen. His concept relied on thin copper wires laid meticulously across a glass screen, carrying a subtle, continuous electrical voltage. When a human finger made contact with the outer glass surface, it absorbed a small amount of charge, altering the local electrical capacitance and allowing the underlying computer system to instantly register the exact spatial coordinates of the touch. This initial prototype was remarkably simple compared to modern glass smart displays. The physical device could only detect a single touch point at a time, possessed zero pressure sensitivity, and could not interpret complex multi-finger gestures. Yet, for the very first time in computing history, the interface eliminated the clumsy mechanical barrier between a user's intent and the machine's response. Direct tactile control over a computer screen had officially been born. Johnson refined his experimental design over the following 2 years, publishing a detailed paper in 1967, complete with circuit diagrams, cross-sectional illustrations, and functional physical prototypes. His refined capacitive touchscreen featured transparent copper wires bonded directly to a cathode ray tube display. Air traffic control operators could now touch an aircraft blip directly on the radar screen, instantly calling up vital flight trajectory data without ever taking their eyes off the airspace monitor. The high-stakes military requirement of airspace defense monitoring demanded unyielding precision and split-second operational reliability. The United Kingdom's radar authorities quickly realized that Johnson's touchscreen invention significantly reduced operator fatigue, input errors, and decision times during intense flight traffic scenarios. The early trials at Malvern conclusively proved that direct surface contact provided an intuitive interaction speed that no physical mouse, trackball, or light pen peripheral tool could ever hope to match. Despite its extraordinary promise, the original capacitive screen faced severe material limitations in the late 1960s. Early conductive wire meshes noticeably obscured display visibility, and the astronomical cost of contemporary mainframe processing hardware restricted widespread commercial adoption. As a result, alternate input methods began emerging in international research laboratories throughout the 1970s, each attempting to solve the fundamental human-computer interaction challenge through entirely different physical mechanisms. By the early 1970s, researchers at the University of Kentucky developed the resistive touch screen, a distinct technological lineage created to automate the recording of high-energy atomic physics data. Resistive systems relied on two flexible conductive sheets separated by a thin microscopic air gap that made physical contact when pressed down. Unlike Johnson's electrical capacitance model, resistive screens reacted to physical pressure, allowing input from gloved hands, plastic styluses, or hard objects.
Tracing this evolutionary transition reveals how interface technology gradually moved from specialized military defense setups into broader industrial settings. Throughout the 1970s and 1980s, touchscreens remained primarily isolated within high-value operational niches, including commercial flight control towers, specialized medical equipment, financial trading desks, and factory automation terminals, where rapid, touch-based data entry provided unambiguous safety and productivity advantages over traditional keyboards. The fundamental genius of Johnson's 1965 insight lay in recognizing that the human body could serve as an active electronic component within a sensing circuit.
By harnessing skin conductivity, Johnson eliminated the need for fragile mechanical transducers or intermediate pointing devices. He converted a static glass viewing surface into an active sensing environment, establishing the foundational spark for modern touch technology that would quietly await its ultimate mass-market awakening. Yet, for decades, everyday consumer electronics remained bound almost entirely to physical keyboards, mechanical buttons, and desktop mice. Bringing direct touch interaction to mass-market consumer devices required miniaturized microprocessors, ultra-durable glass manufacturing, and extremely fast digital signal processing algorithms. The transition from massive industrial radar terminals to portable consumer hardware presented enormous engineering and economic hurdles that required nearly 4 decades of continuous innovation to overcome. The true consumer revolution occurred when microengineers re-engineered Johnson's capacitive framework, replacing visible copper wires with microscopic transparent layers of indium tin oxide. Indium tin oxide provided exceptional optical clarity while maintaining high electrical conductivity across the screen display. This crucial material breakthrough allowed full-color liquid crystal displays to remain visually brilliant while simultaneously operating as exceptionally responsive, high-resolution capacitive touch surfaces. When advanced multi-touch algorithms emerged around the turn of the millennium, the single-point tracking pioneered at Malvern expanded into fluid multi-finger gesture recognition. Pinch-to-zoom, dynamic kinetic scrolling, and multi-touch virtual keyboards transformed rigid glass screens into tactile digital canvases. What began as a specialized radar interface for British air traffic control had evolved into the primary visual and physical dialect of global personal computing. Consider the astounding scale of this historical progression across modern society. In 1965, E.A. Johnson's hand-built prototype sat atop a heavy cathode ray tube in a quiet English laboratory, capable of registering only one single finger tap at a time. Today, billions of handheld smartphones, tablet computers, and public interactive displays utilize that exact same principle of capacitive charge transfer to process millions of complex human inputs every second. Alternative interface pathways could easily have dominated our technological world. Infrared light grids, surface acoustic wave sensors, and resistive plastic films fought aggressively across interactive kiosks, digital organizers, and early handheld computers throughout the late 20th century. However, capacitive touch ultimately conquered the mobile consumer era due to its unmatched optical clarity, scratch resistance, lightning-fast response times, and native support for fluid multi-finger swiping. The origin of the touchscreen reveals a compelling pattern in scientific innovation.
Humanity's most transformative everyday technologies frequently arise from specialized, high-pressure operational problems. Built originally to reduce cognitive fatigue for radar operators tracking high-speed aircraft, Johnson's elegant breakthrough redefined the physical boundaries between human thought and digital computation,
proving that direct tactile engagement was the natural destiny of human-computer interaction. The Royal Radar Establishment's official backing allowed Johnson to secure foundational patents across the United Kingdom and the United States. Although those early patents expired decades before the modern smartphone market grew into a multi-trillion-dollar global industry, historical records firmly attribute the primary genesis spark of capacitive touch technology back to his pioneering 1965 laboratory experiments in Malvern. As modern interface design moves toward spatial computing, augmented reality glass, and direct neural links, the central lesson of 1965 remains deeply relevant. Digital interfaces succeed when they minimize the friction between human intention and computational execution. Johnson's original prototype proved that the most intuitive interface controller for complex
Digital information was not a physical key, joystick, or stylus, but the conductive tip of a human finger. From cluttered radar monitors in Cold War defense facilities to the luminous glass displays held in billions of hands around the globe, capacitive touchscreen technology permanently reshaped how humanity communicates. What started as a simple wire grid designed for high-stakes airspace defense has become the ubiquitous, invisible surface that bridges the physical world with the vast expanse of human knowledge.